All right, welcome everyone. Nice to have you this afternoon. It's 4 p.m. Welcome to this new ING Tech Meetup. And today we'll be talking all things Scala. I'm pretty happy about the meetup tonight because we're having two people, and the first one is Ayush, and Ayush is one of the first people that have been that have been hosting or speaking at the meetup when we started the meetup a year ago. So that's pretty nice. But before that, a few things. Do remember that we have 20 seconds delay between the moment you'll hear something and the moment we've been saying it. So keep that in mind. Please do remember that the speakers, it's very difficult to speak in front of a camera, in front of a screen. We're all at home still. So try to be engaging. That would be really helpful. Don't hesitate to ask your question in the comments. I'll be happy to ask them to Ayush. It really helps the speaker to get the energy going. We will have two talks tonight, mostly about Scala 3. You are welcome to follow along. There will be some live coding ahead. But first, let's go with Ayush. Hi, Ayush. Nice to have you again.
Hey, Julian. Thanks for hosting the event again. Yeah, it's been a year already.
It has been a year. Yeah, just about a year that we're at home.
Okay.
So awesome. I will not take more space than needed. The floor is yours. I will share your screen. You will talk to us about Dotty. So I'm leaving it to that, and see you in about an hour.
Okay, thank you, Julian. Hey, everybody. Welcome to this edition of ING Tech Meetups. Today's meetup is focused on the new version of Scala, Scala 3, popularly known as Dotty. Here at ING, we use Scala a lot, and we are really excited about this new version. So let's see. We have had our cups of coffee, and we are all set, hopefully. Let's make this more interesting. Let's keep the conversation going in the comments. So I'll get started. So my talk is focused on what new types have been, what new types has Scala 3 come up with. And the talk is going to focus on why are these new types important and why we should learn them as soon as we can. So before I start about what types have come in Scala 3, it's good to know what is the goal of having a new version of Scala. Well, there are two primary goals. The first goal is to make Scala powerful and easier to use. We want to make sure newcomers, beginners who are learning Scala find it easier to learn the language. They find it friendly. Also make it powerful. And the second goal is to solidify the ideas of FP. Scala is a functional language, and it is built on the foundations of functional programming. And the new Scala version Dotty aims to further solidify those functional programming ideas. So with these two goals in mind, the Dotty team has come up with a lot of new types. Let's look at each goal and what type we can associate. So to make Scala more powerful and easier to use, the team has come up with a type for enums, and it's a type that was there in Scala 2 with the name of enumerations, but has undergone vast improvements in the Scala 3 version. And this is a perfect place to start. So let's look at enums in Scala 3. This is my Visual Code Studio. This is a simple Scala app. I'm going to use the new Scala 3 syntax with indentations, just like you would have in Python, because it just looks cool. It feels right to be using this syntax. So let's understand about enums in Scala 3. You know what an enum is? An enum is a special class that represents a group of constants. Suppose if you were in Scala 2, you would do something like you would create enums like this. I'm just going to copy paste the Scala 2 code because that's pretty easier. So in Scala 2, you would create enums like this. You would extend the enumeration class in Scala 2, and then you would define enums. So this is an enum in Scala 2. In Scala 3, the syntax is slightly changed and is much comprehensive and easier. You have the keyword enum, then you have the enum itself, which can be anything. I'll call it weekday. And then you define cases for those enums, which are basically the constants that you have for those enums. So I can say case Monday, Tuesday, Wednesday, and so on and so forth. So this is the new syntax for enums in Scala 2, and this was the syntax in Scala 2. So we can get rid of that. So this is how you define enums in Scala 3, that is Dotty. Now, behind the scenes, what the compiler will do is it will create a sealed class called weekday. So remember, we have the keyword sealed. The compiler will create a sealed class for weekday, and all these values, all these weekdays, Monday, Tuesday, Wednesday, will be present inside the companion object. So this is equivalent to doing something like this: sealed trait weekday, and then creating object weekday, and then defining case object Monday, and so on and so forth. So enum takes care of creating this sort of construct for us uh, by default. Now let's look at why someone would be excited about enums and why we would use enums in Scala 3. But before we do that, let's look at some methods that we have on enums. Let's suppose we want to get a particular constant from the enum set. What we could do is we could say weekday dot Monday. Once you have a enum, you can call many methods. You can call ordinal, which is basically the unique value of this enum, the integer representing the unique value. You also have a method called weekday dot values, which will give you array of all weekdays. So this is pretty simple. Something that was also there in Scala 2 enumerations. Let's look at what special things do we get with Scala 3 enums. Enums can be parameterized. So you can do something like this. You can say enum result of type error and type value. And then you can say there is a case of success, and it can have a T of value, where value is a parameter type here. I'll just call it val. And you have to use the keyword extends to say that it is one of the types of the result. And you can say there's no error and there is a value. Similarly, you can have a case for error, which can be just the counterpart of the success. So like this, you can also parameterize enums in Scala 3 like this, and you can provide a value, and you have to use the extend keywords to supply the value. So here we are using the keyword extends to indicate the type that the result have. There is no error and the value is of type val. And if you have an enum like this, you can create a success. You can say success is equal to result dot success 1. So what this gives me is basically a result of this can be anything, and this is basically int. Yeah, this is any. So this is how you can also parameterize enum. Now, as I said, one of the goals was to make Scala 3 a lot safer and a lot easier to use than Scala 2. So let's look at what improvements do we have between enumerations that were present in Scala 2 and the enum in Scala 3. What advantages do we get when we use Scala 3 enums? Okay, so if uh, I had a Scala 2 enumeration, and I'm going to copy that enumeration so that I don't have to write Scala 2 code. So let's suppose we have an enumeration called season in Scala 2, and suppose this is the enumeration. Yeah. Now suppose in this Scala 2 enumeration, I wanted to add some properties to this enumeration season. There can be multiple seasons. There can be winter, summer, and so on and so forth. I want to provide properties like I want to say number of days. How many days are there in a season? I want to add this property to the season type. The syntax in Scala 2 for doing that is quite verbose and requires a lot of code. I'm going to again just copy that syntax from my Scala 2 code. So this is how you would do it in Scala 2. What you have to do is you have to define a inner case class inside, which extends the val. This inner class can take properties that you want. So I wanted two properties. I wanted days and I wanted months. I can provide these properties to this internal class. And once I have this inner case class, I have to then write an implicit converter that takes a value of enumeration and returns this inner class. So this whole piece of code that you are seeing here is basically to add properties to an enumeration in Scala 2. Obviously, this seems way too complex than anybody would want it to be. So what we are going to do is we are going to comment this out. We are going to forget about this now, and we are going to see how we do it in Scala 3. In Scala 3, we'll create an enum called season, and then we'll basically add to this season enum the properties that we want. So we want days, we want how many days the season is long, and we want suppose the month this season has. Once we have this, we can write the cases of this. So we can say winter. You have to use the word extend. And we'll say winter lasts for 90 days and is from December to February. Similarly, we can add a case summer, which extends again season. And again, we'll say it has 90 days and suppose it goes from June to August. So if you compare the two syntaxes, you will find how less verbose and how clean the syntax to add properties to an enumeration in Scala 3 is. It's way simpler when compared to Scala 2 and looks very nice to the eye also. Not only this, you can also add a general purpose case. You can say other season, and you can make it parameterized. So you can take this takes an int and a month as input, and this extends our season. And you can pass the days and the month. What this allows you to do is basically not only you have handle to constant seasons, so you can say summer is basically season dot summer, but you can also create new seasons at runtime and you can pass the properties as you want. So I can say, okay, let's suppose I want to create spring. So I can say season dot other season and I can pass, okay, spring is again for 90 and yeah, it's from March to June. So this basically is a very nice way of creating new types at runtime using an enum. And not only that, you can also add your own member definitions to this enum. So I can add a member definition like say duration, and I can say, okay, this duration is a string, and I will say, okay, it has these many days and is this much long. And then I can use the member as I want. So in this case, I can just print it and I can say spring dot duration. And if I run this, then you should see what we expect. It's 90 days and it's from month March to June. So yeah, this is one problem that gets solved with Scala 3 enums, that adding properties is very easy. It makes it very easy to add new properties, to add new member definitions to your enum types. The second problem that it solves is about pattern match. And let's see this in practice now. Again, I'm going to copy a Scala to enumeration. So this is a Scala to enumeration. It's a contract type, and we can have a permanent contract or a temporary contract. Let's suppose I have a contract type handle available in my code somewhere. This is contract type dot value. Let's not worry about where it comes from. But suppose if I apply pattern match on this contract type, if I do this, now ideally there are two contract types that I can see, permanent and temp. So I should be pattern matching on both of them. And suppose for some reason I was lazy and I forgot, or I just did a pattern match on one of them. I did not do a pattern match on the temp type. I don't have the second case here, which should be matching for the temp type also. Scala 3 and even Scala 2 does not give me any warning. You see here is my warnings list, and I don't see any warning coming here about missing case statement for the temp type. So this is a problem, especially for functional programmers who extensively depend on the type system safety. Here, the compiler is not warning us about a missing type match here. It's not telling us anything about that. Now let's do the same thing using a Scala 3 enum, and let's see if that changes. So I can, instead of this, if I change it to enum contract type, and I say there is a case permanent and there is a case temp, and yes, like this, and I have a contract type here. Now you see immediately I get a warning from the compiler that match is not exhaustive. It may fail on case temp. So Scala 3 enums are more type safe as you would expect them to be, that the compiler will tell you if you are missing a match on any of the possible values that you have on the enum. So this is a wonderful addition that Scala 2 enumerations were lacking, and yeah, a pretty bad one too. So we have what we call as exhaustive pattern match is present in Scala 3 enums. Another issue with the Scala enumerations in Scala 2 was about type erasure. And let's see what the problem was. Again, let me just copy some Scala 2 code. Let's look at this. So we have two enumerations defined. There's a color enumeration and there is some other enumeration. These two enumerations are not linked to each other at all. One is of type color, one is some totally other random value. Now if I define a function called print, and I pass this function a color value. So I'll say colors dot value, and the implementation is not important. Let's just return unit. And suppose I define one more function now, which is again print, but this time I pass it the other enum. So I say some other dot value. So if you look at it, these are two functions that ideally are overloaded in their parameter type. This takes a color value and this takes some other value, and they are not related at all. But I already see a problem in the compiler that it is not allowing me to write these two functions at all. It considers them to be same type. It considers that this print method, which takes a color value, and this print method, which takes some other value, to be of the same type totally. It says here that you have conflicting definitions for the print function. Now that happens because the compiler, after seeing this code, basically does a type erasure. And after type erasure, both these values, color dot value and some other dot value, they all end up being the same thing, which is enumeration value. So both these types have the same type after the erasure, and it is enumeration value. And that is why this is not allowed. You cannot have these two functions present in your code. And yeah, this does seem to be a bit worrying, that you cannot have two functions that take two different enum values. On the other hand, if I change this to a Scala 3 enum, and if I say this is enum of colors, and again for Scala 3, I'll use the new syntax. And I say this is case red, green, blue. And if I have similarly the other enum, and I remove this, and I say this is some case ABC. And I add the indentation required, and then I create two functions like this, then there is no problem at all. The compiler does not complain about there being two functions which one takes a color and one takes some other enum. And that is because internally these enums are not represented using enumeration at all. This is basically a class in itself, and this is a class in itself. And that is why there is an additional type safety check present for our code. So this also helps. So we have also solved another problem, which is of type erasure when we use Scala 3 enums. Okay, moving on. The other benefit of using Scala 3 enums. What the concept of enum is mostly popular from languages like Java, which have support for enum also, and they have a lot of methods in Java enums like compare and name and so on and so forth. And Scala 3 enums have a property that you can basically extend your Scala 3 enums to work like Java enums. And the way you do that is by writing something like this. So suppose you have a enum day and it has two values, say a good day and a bad day. And you want this enum to work like a Java enum or to support properties that a Java enum does. You can basically say that this enum extends enum from Java, and you have to pass it a type, which is the day type. And once you do this, you get all the members or properties that a Java enum has. So I can say if I have a good day, I can get the name of that. And this name is a property that is present in the Java enum and not in the Scala enum. So I can call the name member I can call other members like compare to, and I can pass the other possible values of enum. So I can say compare to bad. So these methods like name and compare to, they are actually coming from the Java enum type, and that is because we have extended the Java enum here. So this is also pretty cool that we get with Java enums. I'm almost coming to the end of my session for enums. So if there are any questions, you can already start writing them in the comments and we'll pick them up. The last thing I wanted to tell about enums was how well they are suited to write ADTs. So ADTs we know are algebraic data types, and you must have seen a lot of data types already in Scala 2, like options or ethers. Enums in Scala 3 are a perfect candidate to model your ADTs. And let's take an example to see that. Let's see if I can rewrite the option type using enums. So we know what option is, right? We have this keyword option in Scala, which is this thing. So we have this awesome type in Scala called option, and it is implemented using a case class concept where the option type itself is an abstract class, and then it has two subtypes, some and none, which are case classes. Let's create a similar type as option, but instead of using case classes, let's use enums. So let's say I define my enum as option enum. It takes a value, it takes a type t, and this is a covariant type, so I say plus t. Then I need to provide two cases. I can say first case is sum. Again, it's covariant on t. It has a value t, and this extends option enum, and I can pass the type t here. The other case is none, which extends option enum of again nothing. So this is how you can actually write option in Scala 3, and you can even define methods if you want on this type. So you can have methods like def exists, which return a boolean, and you can write this method on this type, and you can say this match. If it's a type of sum, then return true, otherwise false. So you can write properties like this, and you can instantiate also. So you can say opt enum option enum of int is equal to option enum dot sum 1. By the way, if you don't want to write this option enum every time, you can use something known as export. So you can say export option enum dot everything, and then you can simply do sum like this. So the enum introduction in Scala 3 is a great step in making Scala more safe and easier to use, especially when you wanted to use the concept of enum and creating constant values. Julian, are there any questions that we can take up right now?
I think there have been a lot of discussions, not so many questions that haven't been answered, because Alexandru has answered some questions.
Oh, awesome.
There is one question from Nicola about what features of Dotty you're excited about. But I think this is just the first part of your talk, right?
Yeah, if there are any questions about enum, then we can probably look into them. Otherwise,
there has been a discussion about the fact that the enum name was not so well chosen because of the confusion with Java.
Yeah.
Most of the other questions have been answered.
Yeah, The jury is still out on that one, whether the name fits.
Okay. Do
Okay.
you know what other suggestions are?
I think it confuses with the Java enum type. So
Yeah.
one suggestion was to deprecate enumeration and name this thing as enumeration itself. But yeah, then you would have issues with compatibility.
Okay.
Yeah.
Okay. Thanks.
Okay. So we
You can
saw.
continue.
Okay. So we saw one of the constructs or the new types, which is enums, which makes Scala powerful and easier to use. If you have doubts on enums, you can just ping them on the comment section. We'll take them up. And for now, we'll move forward to the other goal of the Dotty compiler, which is to solidify the ideas of functional programming. We want to make sure concepts like dot calculus are strengthened in the new version. And for achieving these goals, there have been two new types introduced. The first of them is union types, and the second is intersection types. So let's go ahead and explore union types and intersection types in detail, and let's see why these types are beneficial, why would someone use them in their code, and why are we excited about them. So let's go to our, let's look at intersection types first. They're more interesting. Okay, so what is an intersection type in Scala 3? Let's understand that by taking two types. Again, I'm going to use the Scala 3 indentation syntax. Looks nice. Suppose we have a trait called readable, and this trait has a method called read, which returns unit. And suppose we have a trait called writable, which has a method called write. And this is something that is pretty normal. You have two traits, and these traits have properties of their own. A readable trait can read, and a writable trait can write. Watch what I'll do here. I'll create a new type. I'll call it both. And I will say this both is basically readable and writable. So this new operator that you see in the middle, this AND operator, is how you create what we know as intersection types. So both here, the both type is an intersection of readable and writable. Any variable which has a type both has properties of reading and writing. And let's take a example to understand this. Let's suppose I create a function called def fun, and I pass it a parameter p, which is of type readable and writable. Now in this function fun, I have access to my parameter p. P can read and p can also write. So the parameter here, which is of intersection readable and writable, is having properties of both the readable trait and the writable trait. And that is what intersection types are all about. This is a type that has the properties of intersected types at the same time. Now, one would argue that in Scala 2, you could do something like abstract class C, and you could say extends readable, and there was a keyword called with, and you could say with writable. And then you could create types of C. So you could say val C, and C also could read and C also could write. So what is the difference between having an intersection type and a type that is created using the with extension that was also present in Scala 2? Well, intersection type is basically an enhanced version of the with type. The with operator in Scala 2 was not commutative. And as you know, being commutative is a very important property in the algebraic world. So what I meant with that was in Scala 2, A with B was not same as B with A. This was the case in Scala 2 that A with B was not same as B with A, but A and B is same as, or yeah, we can use this operator, is same as B and A. So that is the difference between using the with operator and using the intersection type. Although in Scala 3, the with operator is implemented using the AND operator, so there is no difference, in fact, in Scala 3 if you use with or AND. But in Scala 2, at least, the with operator was not commutative, whereas the intersection type introduced in Scala 3 is commutative. And we will see this with an example that how this commutativeness helps us. But for now, let's have some look at some basic properties of how intersection types work. So let's take an example of what would happen if the two intersected types have same members. What I mean by that is, suppose we have a trait called reader resource, and this has a member called get, which returns a reader. This reader is what we just defined above. And suppose there are another trait called writer resource, and this has a member called get, which returns a writer, a writable. So this is readable. Yeah. Now suppose we have two traits like this, and we have a method which takes an intersection type read write, which is basically reader resource and writer resource. Now both of these types, the reader resource and the writer resource, have a method called get, but they are returning different types. The get in reader returns a readable, the get in writer returns a writable. Now if I call the method get in my intersected type, what will I get? Will I get a readable or will I get a writable? Well, the answer is that because it is an intersection, you will get a type which is again an intersection of these two types. So basically what you will get is a readable and a writable. So basically if you have two types and they have the same members, an intersection of these two types will return intersection of what the members return. So because these are returning readable and writables, the intersected types returns an intersection of readable and writable. So the idea is that if a members appear in both A and B, its type in A and B, so the type of get in reader resource and writer resource, would be the intersection of its type in A and its type in B. So it's an intersection of readable and writable. So that's the way to look at it. That's the way how this problem is solved. Oh, let's take another example now. What happens if they both return the same type? What happens if this also returns a unit and this also returns a unit? What happens in this case? Then what does the compiler do? Well, as you can see, if I have two types that return this, that have the same members, the same signature, and if I create an intersection of these two types, I can still call the member. There is no issue with calling the member. The compiler does not complain at all. There are no errors here. And the reason behind it is that the compiler does not have to worry about how this implementation will come. That is a problem that has to be solved when you create this type. It is not a problem at this point of time. At this point of time, the compiler has no issues in saying the get method will be called and it should return a type of unit. Whether it will be this which is called or whether it will be the other one which will be called, that is something that has to be solved when you actually call the get method or when you create this instance. So if I create a class like C extends reader resource with writer resource, it is at this point that I have to tell what type I should define. Let's use another type D. So if I do something like this, then the compiler tells me that you have two members and you need to tell me which member should I call. So I can say, okay, let me help you with that. Override def get, and I can provide implementation here, or I can do whatever I want. So I hope you get the essence that if the members have the same types and the return type is also same, then the compiler will not complain about calling the method on the intersected type. It's only at the creation of the intersected type you need to decide which of the members you would like to be called. All right, so this was a deviation into what is known as the diamond problem in Scala, but that's for a later session. Let's move on. Let's see some properties of intersection types. The first property, which is pretty obvious, is that if you have two types A and B, then A intersection B is a subtype of A and is a subtype of B. If I write it down, what I'm saying is A intersection B is a subtype of A and also is a subtype of B, and which is pretty obvious, right? Because suppose if I have a trait A, then if I have a trait A and if I have another trait B, and if I have an intersected type AB, which is A and B, now the type AB has properties of both A and it has properties of B. So if I have a value which is of type A, then I can assign it AB, because whatever I expect from A is basically also present in AB. It has A and B both, and similarly the same goes for B also. So if I have a type of B, I can assign it to AB because AB has properties of both A and B. So this is pretty nice property and easy to understand that intersection types are subtypes of their original types. The other property that we were talking about was about commutativeness and why the with operator was not commutative, but the intersection operator is. And let me copy an example and let me show what I meant that time. Okay, let's see these examples. So suppose, yes, suppose we have a trait called, let's highlight this section, commutative property. Suppose I have a trait called parent, which has a method foo, which returns anything. And then I define two extensions of this trait, E and F. E returns int, and int is a subtype of any, so this works. And F returns any, and it just returns a dummy value. Now in Scala 2, what would happen is that if I create two types, if I call the method foo, I can call it two ways. I can say val foo1 is basically, if I had a type of E with F dot foo, or I could say val foo2 is equal to, I have a handle to F with E and I call foo. Now in Scala 2, you would find it surprising that foo1 will actually be of type any and foo2 will be of type int. That is the way it works in Scala 2, that in Scala 2, foo1 is of type any, and in Scala 2, foo2 is of type int. And that is breaking the property of commutativeness, because that means E with F is not same as F with E. However, in Scala 3, the with operator is deprecated, and instead you can use the and operator, because internally with is also implemented using and. And in Scala 3, basically you have both of these as type int. Both foo1 and foo2 will have type as ints. But that was not the case for Scala 2 at least, and this is a definite proof that basically A and B is the same thing as B and A, which was not the case if you were using the with operator. Are there any questions up to now in the intersection type? We'll keep discussing, but if you have any question, feel free to post. Maybe Julian can.
Yeah, I'm here. As far as I can see, there is no questions about the intersection type that you haven't answered yet. There was one question about the difference when creating ADTs. Oh, let me put the question on screen, that's easier. What is the difference when creating ADTs with seal traits and case classes versus enum? So it's an enum question.
Yes, Nishant, actually, if you use enums, you would get the same level of type safety and the same level of expressiveness as you would get using sealed traits and case classes. And that is because internally, enums are also implemented using sealed classes and objects. So whenever I create an enum in Scala 3, the Scala compiler behind the scenes is creating a sealed class called weekday and creating a companion object for us, which contains these values Monday, Tuesday, and Wednesday. So you would get the same level of abstraction and the same type safety using enums and using the sealed trait and case class pattern. It is just that the enum construct is less verbose, and yeah, you write less amount of code. And that is why you would prefer using enums instead of ADTs.
Okay. There are some additional questions, but they are more generic to Scala 3 versus Scala 2 and things like that. So I think at the end of your talk, I'll do a joint Q&A about that with Alex.
Okay,
Keep
awesome.
going.
Okay, so this was, we were discussing about intersection types and how intersection types work fine. Now the question is, why would you use I mean, in Scala 3, if the with operator is same as intersection type, what would be the benefits of using these types basically? So basically, you don't have to create a new type. So if you want to say, I want properties of both A and B at a given time, you can directly write a method like this. You can say def my method, and you could say it takes a value A, and this value A should support values of type A and values of type B and values of type C and values of type D. You could go on and on like this. Now, this was something that was not possible, at least with the previous versions of Scala, because you would have to come up with types. You would have to say type common, and you would have to say A with B with C, and or you would have to write things like that. So that is something that you get saved with if you use the intersection type. Yeah. So and we saw that they are commutative, which is a very good advantage when it comes to implementing Scala laws. The last part I want to mention about intersection types is when it comes to how they deal with variance. And I will take an example to demonstrate how variance works in intersection types. So suppose I have a trait called employee and I have a trait called manager, and I have a employee repo which basically returns me employee by ID. So I pass it a ID and I get an option of employee because yeah, it's possible that the given ID has no matching employee. And similarly, I have a manager repo which has a method again get by ID, takes a ID and returns again an option of manager. Now what happen if I intersect these two repo types? What happen? Let's see if I have a type which is employee repo and manager repo. Let's not concern about where this value comes from. Suppose now I call the method x dot get by ID and I pass some ID. What is the expected type of this result? So the employee repo gives an option of employee and manager repo gives an option of manager. And what we saw in one of the previous examples was that when we have two members with the same name, the return type is basically an intersection of these two types. So basically the result type is an intersection of option of employee and option of manager. This is the return type basically. But if you look very closely, option is covariant in nature. And given that option is covariant in nature, option of employee and manager is basically the same thing as option of employee and manager. Now you can think about this, but this is again something that you can derive if you have the laws, but it's pretty obvious also that the type on the left hand side is an intersection of option of employee and option of manager. So the possible values are, for the left hand side, it can be a none, it can be a sum of something x, which is an employee and has to be a manager also. That's the only possible values I can give to this type. So what I'm saying is if I have a variable of type X and it is of type this, now X can only have uh, uh, X can only have some possible values, and they basically, or let's call it something else, it can only have two possible values. It can either be a none, this xy can either be a none, or it can be a sum, but that some type has to contain both the values, because when I do an xy dot, suppose do a map, the value that I have inside, if you check carefully, it is an intersection of employee and manager. So that means this type inside this sum has to be an intersection of employee and manager, which is the same thing as having an option of employee and manager. So basically for covariant types, what I'm saying is if you have a covariant type C, then C of A intersected with C of B is the same thing as C, A, and B. These are the same things. This is a property that is true for intersection types when C is covariant. And you can take any covariant type. You can take a list, you can take option, the same property will hold. Okay, please feel free to ask your questions on intersection type in the comments, and we'll move on to the next type meanwhile, which is the union type. Let's look at what is a union type in Scala, this is more simpler than intersection type, although it's more interesting. And Yudian can let me know if there is any questions and I can take them. And meanwhile, I'll continue. Yeah.
No questions. I'm here, but no questions.
Okay. So a union type is represented like this. Let's say I have a union type which is a string or int. It is something like using the pipe constructor and saying this. So basically, string or int variable represents a type, this type, string or int. It's a type that has values of type string or unit at a given time. So when I create this, I can either give it a string type, this is valid, or I can give it a unit type, that is also valid. So this can hold values only one at a time, but it can be either a string value or a unit value. Intersection types, on the other hand, were holding values of both the types at the same time, while union types are holding only values of a given single type at the same time. Now, if I have a union type, then I cannot directly say, okay, I don't have any members that I can access. I cannot access members of type string or int. In order to access those members, I first need to extract the right type from my union type. So for which I can use a pattern match. I can say string or int match, and I'll give this time a type int because it's an int and not a unit. So I'll say string or int match, and I will say if it's a case of string. Once I'm inside this case statement, then I have the handle to the string type. I can do two uppercase, two lowercase, whatever. I have access to the string type basically. And you see, if I don't write all the possible pattern matches, then the Scala compiler will already tell me that my match is not exhaustive. So I have to write the other case also, which is an int, and have to handle this also. That is something that I have to do. Now, this type can have not just two, but it can have more than two types. So I can have a string or int or double or float. I can have as many types as I want. It is not restricted to only two types. You can have a union of as many types as you would like. So that is pretty nice to have. What else? So uh, the main advantage of having union types is that you can basically write your code without declaring extra types. So suppose I have a function that works on that. Suppose I have two classes, class A and class B, and I have a method, say print, and this could take A or B. It works on both. In Scala 2, I would have to create a type and then use this, but in Scala 3, I can say it takes A or B directly like this, and then I can write the method. So creating types becomes very easy if with this union type construct. The other property of union types is that they are commutative, which means that A or B is the same thing as B or A. These are same constructs. So if I have a var A or B, and I call this, say I give it new A, because it can be either A or B. And suppose I have another var which is B or A, and I just reverse the types order and I say, yeah, this is again new B. Then I can assign one to other very easily. I can say A or B is equal to B or A, or I can also say B or A is equal to A or B. So this is possible if I use intersection types. Sorry, union types. So this is basically the commutative property of union types, that A or B is same as B or A. So if you say one or other, it does not matter. The other advantage of having union types is that they are also very interesting when you want to use covariant types. Let's take a covariant type and understand how it would work. So suppose I have a trait called printer, which is covariant in nature, and it has a method called print. For now, let's not worry about what this does. Suppose I have a trait like this, which is covariant, which is contravariant, sorry. Now let's see how contravariance will work with union types. Suppose I have a type of int printer, which is basically a printer of int. And suppose I have a printer of string, which is basically a printer of string types. Again, not important how we get the implementations, just trying to understand the concept. Now, if we have a type intersection between these two types, so if I have a printer that can print either of them, so it can print a string or it can print a int. If I define a printer like this, then what I'm saying is basically this printer, because of its contravariant nature, can print a string or it can print an int, which basically means that I, I can assign its value to a printer of type int, that it can print either string or it can print int. That is something that is possible here. I will just name them as var so that the assignment is allowed actually. Yeah. So basically what I'm saying is a printer that should print int values can be derived from a printer that can print either string or int, which doesn't make sense. And similarly, I can say if a printer that should print string value can be derived from a printer that can print either a string or an int. So basically what we are saying is that for contravariant types, C of A or B is a subtype of C of A. This is the property that we are trying to prove here for union types with contravariance. And the same goes for B. If there are any questions, please feel free to write them on the chat and I'll continue meanwhile.
There is one, but I'm not sure you can answer it without context. Baris is asking, does it mean that while using intersection type, if we map, we will have tuples of a tuple of data?
Let's take an example of that. If I have an intersection type of an option, suppose if I say val opt is an option of string or int, I don't care what it comes from. So if I do opt.map and I see this value A, let's check out what A is. So A here is basically a string or an int and you don't know what it is. In order to get this, you have to do a match again. Once you have the match, then you can perform the right operation.
Okay, so it's a bit more complex than a tuple.
Yes, it's not a tuple. Union types will only have value of one type. It can either be a string or an int. It cannot be both. A tuple would mean that you had something like _1 with string and _2 with int, but that is not the case. A here can have values of either a string or an int. So A is basically a type of string or int here. To get the actual value, you have to do a pattern match.
Okay.
Yeah.
We have another question from Alexandru.
Okay.
When would you use enums? When would you use enums, and when would you use untagged union types?
I think when my domain has a requirement for mapping ADTs, I would go for using enum types. I am not sure about untagged union types. I've not explored those at much. I can say for sure that if I have to explore ADTs in my domain, I would use enums. But I'm not sure about untagged union types, if they would be a fit for mapping ADTs as well.
Okay. Thanks. We can continue.
Okay. Okay, so we were looking at this peculiar property that if you have a contravariant type, then the contravariant type A or B is basically a subtype of contravariant A. Basically, whenever you need a printer of int, you can supply a printer that prints either string or int, and the same goes for string also. Now, a bigger question is that how can we create this type? How can we create a printer of string or int? Let's try to create that. We can either just create it like a normal implementation of the trait, we would say it is a printer that takes these, and here I would do implement the type actually. So I would then, so this is how I could create a printer which prints string or int, and this is how I could implement it. This is one way of creating this either printer. Another way of thinking about this is, what if I have these two printers of type int and string? What if I joined them? What if I made an intersection out of them? So what I'm saying is, if I create a print both, which is basically a intersection of the two printer types, what if I had this type present, which could print both? Now, this also satisfies the same constraints that we are expecting from print either, because what we are saying here is that this is a printer that can print either string or int. And what we are saying for print both is that this is a printer which has properties of both a printer of a int and a printer of a string, which is basically the same thing, right? And that is exactly true. So you can basically say that P either, which is something that can print an either or a string, is derivable from something that prints both, and the other way around is also true. I can say print both is same as print either. So what I'm saying here is, if I have a contravariant type C, then C, A or B is basically the same as saying C, A and C, B. So printer of string or int is same as a printer that has properties of printing int and a printer that has properties of printing string, which gives us this nice law that for contravariant type C, C, A or B is the same as a C of A and a C of B. But remember, only for contravariant types. Okay, so that brings me to end of my explanation for union and intersection types. Are there any questions that I can take?
I don't think there's any questions about unions and intersections. There are some questions. Oh, plug your Mac.
Yes, exactly.
There are some questions more generic. Alex wants to come in. Yeah, Alex, I can put you in. There you go. Go for it.
Yeah, I asked that question, when would you use untagged union types versus enums? By the way,
Yeah.
untagged union types, this is a really theoretical, it's a theoretical, let's say, how do you say it? Term? I'm probably going to butcher the English language like tonight, but so enums are tagged union types, tagging because the runtime knows what those values are, and untagged union types, which is the unions that you're presenting, is basically bring your own tag, right? I mean, you're doing like is instance of, for example, that's a tag that you're going to use because you know that the Scala compiler will know what to do with it. But when you have type erasure, things get more complicated, right? So untagged union types are not good when you're describing generic code, for example. You can't, when you have an A or a B and they are type parameters, generic type parameters, you can't differentiate between them. But otherwise, they have, let's say, no runtime overhead. right? So that's the big difference, and it's basically about bringing your own tag. TypeScript programmers love it. So, and I'm really excited about Scala's and tag union types, even though people don't know what to think of them. So, yeah, I'm off right now.
Okay. Are you done with your talk, Ayush?
Yes, and I wanted to extend to what Alex said. So a lot of these new types are basically motivated from what has been there in another languages like TypeScript, as Alex mentioned. Intersection types and union types, they're present in languages like TypeScript, and the Scala team has probably been haunted by all of us to add these to Scala as well. So yeah, great additions to the Scala new version.
Okay. Thanks. I think if you're done, Alex, actually, I would like to have your input as well, because we have some generic questions which we maybe can take as an interlude between the two talks. So if you want to join again, otherwise, yeah, there you go. Let me add you. There you go. And I will hide your screen. And let's ask a few generic questions about Dotty itself. Let me find them. The first one is, what are the features of Scala 3 that gets you excited?
Oh, that's a great question. Well, Scala 3 has proper syntax for tag union types that Ayush presented. Those are the enums that he presented, right? Untagged union types are nice because, well, one thing that allows us to, what untagged union types afford us is to describe null. So null is like a scourge on the Scala language. But now we can describe it with untagged union types. So we can say A or null, and we can do strict null checking, which is what Kotlin has been doing, right? But the mechanism in Scala is more generic. We can use it for other untagged union types as well. One great thing about Scala 3 is the macros. So they cleaned up the macros. Basically, in Scala 2, library authors have been dealing with macros, and they are awful because they are exposing the unwashed compiler internals. So if you want to crash the compiler and see how crashing the compiler looks like, yeah, you use a macro or you use a library that uses macros. They have been cleaning up the macros, but on the other hand, the macros are right now more restrictive in what they allow you to do. You can also do type class derivation, which I'll get into tonight. Macros are the biggest thing because they complicate Scala 2. Right now it's a cleaner language. I hope it is a cleaner language because I haven't used it in practice much. But yeah.
All right. Thanks. Do you have anything to add, Ayush? Is there something else that you're?
I would like there is a feature called explicit nulls in Scala 3, which basically changes the hierarchy of the system. Currently, null basically is a subtype of any ref, so you can have reference values like strings or your own types with null values, and that can lead to strange behavior. You might not expect a string to have null, but it will throw null pointer. But with explicit null feature in Scala 3, null becomes a subtype of any, and then you cannot assign string or your own custom type nulls values. So you save a lot of headache, especially with null pointers. That is one feature that is very exciting. And other part, as Alex mentioned, is about the meta programming, which is macros and stuff. That is something to look forward to.
Okay, thanks. I have to look up what macros are. I don't even know what you're talking about, to be very honest.
If you don't need them, don't look them up.
Okay. And the second question from Nicola was, do you guys have any experience migrating a Scala 2 to Scala 2 code base to 3 yet? Is that something you looked into?
That is something we are looking forward to, because a lot of teams because there's a lot of dependency between teams in Scala libraries, especially the frameworks that we use here at ING. So I would say not yet, but yeah, we will see what experience the community has.
Okay.
Yeah, so there's by the way, there's like the Scala community build, which is like a big set of Scala libraries that are popular and compiled, and they're compiled already on Scala 3. But the effort of migrating libraries is ongoing from the ecosystem. For example, Cats has been migrated, but something like Akka might take longer, because Akka usually takes longer to migrate to new major Scala versions, let's say. And at ING, for example, we are using Akka, so we might wait a while. And just to mention, Scala 3 is not ready for production yet. It's at release candidate 1. So it's nearly there. It's going to be released soon, and there's an ongoing effort in the ecosystem to migrate to Scala 3. And if you want to help out, by the way, now is a good time. But yeah.
Is there any backwards compatibility, or is that going to be like Python to say the very bad thing?
There is.
Okay.
There is a backwards compatibility when you move from Scala 2.13.4 to Scala 3.
Okay.
So there is binary backwards compatibility, which is a new thing in Scala, because major Scala versions aren't binary backwards compatible with each other. Going forward, they introduced Tasty, which is like an intermediary format when compiling binaries, and the hope there is to like divorce the compiled artifacts from the Java bytecode, such that going forward, binary compatibility might be better. I don't know what's the effort on that. But yeah, there's going to be binary compatibility with Scala 2.13, so we can use that. But I would migrate our projects, for example, our production projects, when all of the libraries have been migrated officially. So.
Okay, thanks. There is a last question I'll pick up now before moving on. And it's a little bit of a specific questions, but there's some question about a JSON parser in Scala 3. Do you know of a JSON password?
Serke added support for Scala 3, but I need to check that out, because yeah, this was being discussed in the community. Yeah, so if you see the releases, let me paste this.
So maybe you can put
paste
a comment
this on the chat.
Yeah.
Yeah. So if you see the releases page here, they already have support for Scala RC1 candidate. So yeah,
put that in there. Okay, thanks. Oh, here it is. All right. I suggest we continue. So Ayush, as I understand, you're done, right? We're moving on to Alexander. Okay.
Yes.
So let's move on. I will hug you. Thanks for joining. I actually I haven't done any Scala for 2 years, and it's quite a refresher. So that's very nice to see that the Scala 3 project is moving forward. Thanks a lot. See you in a year then, and hopefully not online. All right. Cheers. Alexu, second speaker of tonight. What's nice about those meetups is that actually I don't know Alexu at all. He works at ING, he works at ING Romania, and somehow when I check him up when he wants to speak, I realize that he has 4,000 followers on Twitter, that he writes his own libraries, and he's a committer of very big libraries from the language Scala. So that's super nice to realize that we do have people like that. I will not take more of your time. I think you're just ready to go, Alexu. I'll let you introduce the topic yourself. All right? And if you need me, just let me know.
Yeah.
Oh, I do have one question. Do you prefer to have your head or not? Because you were asking to not have the... Do you prefer me to leave your head on the left, or do you prefer to not have your face at all?
No, let's leave my head.
Yeah? Okay.
Yeah.
I need you to share your screen. I can't see your screen now. All right.
Wait. Okay. Allow.
There we go.
Can you see my screen now?
Yes. Let's see. Ooh, boom. There we go.
Yeah.
All right.
I'm not going to be able to see any questions because I'm an old-fashioned guy and I'm using a single monitor. So I will stop myself and ask if there are any questions. Yeah. Hi. This being the pandemic, I'm thinking of showing my head because, we are online all the time and we might as well see each other's expressions. I'm at home and you might hear my fabulous noises. Yeah, so today we are going to talk about type classes in Scala 3. Scala 3 introduces some syntax changes, making type classes easier to express. And it's pretty exciting because in Scala 2, we kind of struggle with the encoding there a little. We can express type classes in Scala 2, but Scala 3 makes this better. And I think we are going to see more type classes in our projects, let's say. And I'm going to take this opportunity to also introduce maybe some best practices in the process. I wasn't sure of the level of my audience, so I prepared this presentation for Scala beginners that want to learn about type classes, about implementing type classes. So let's get started. We are going to first start with simple type class definition. Let's say that we want to concatenate things together. And I'm naming this concatenable such that I don't scare people away. This is going to have a method called concatenate that's going to have take another parameter. And this is like the OOP version. We take a concatenable and we return a concatenable. And I just had a presentation about this at Scala Loves conference. The list scope substitution principle doesn't work here. Type classes are often about composing types. So when we combine two objects together, in this case, we care about the type. Right, so we concatenate two strings together. We don't concatenate a string and an integer because this isn't JavaScript, right? So we care about the type, and we start by introducing a type parameter here. And then we can describe. Concat takes an X and a Y and returns an A. And now it's all nice and type safe. This, I believe, yeah, it's fine. And now let's define some utilities here. Let's do something useful with it, right? So let's start with a list of A's. And we want to concat them all up. I hope that my keyboard is not too loud there. Now, what can we do with the list? We could fold left it. And we need to start from somewhere, right? So we'll need some sort of empty element or 0. We'll just add this to our interface, right? Now, in order to add this as a restriction, so right now our signature is totally generic, right? We know nothing of A. Well, A in Scala is inheriting from any, so it has stuff like hash code and equals and toString, but we are functional developers, so we are not going to use those. Now, in order to add a restriction to this A that we require concatenable, we are going to use this new keyword from Scala 3, which says using concatenable of A. So we require an instance of concatenable. By the way, this is like the old implicit, right? We require an evidence via the implicit keyword, and this would require that there is an implicit instance in scope, right? Defined for that A. So this is like the same thing. We can say using concatenable, and we can also give it a name in case we want to capture it as a value that we can use here, which we are going to do, right? Concat. And now, what happened? Okay, yeah. Empty f concat. So we start from empty, and then, in case you don't know the signature of fold left, this gives us our state, and then the current element, and then we can concatenate it. I just used like something close to point freestyle there, but passing that function as a value. I hope this makes it clear what I just did there. Now we are just not going to pretend that this is like a no-op interface, so we are going to give it like its proper name. This is a monoid. I learned about monoids in my high school, by the way. I don't know why people complain about that name, but you know, like in Romania, school is following the French and Russian models, so we learned weird things. Anyway, so this is basically like an algebraic structure that has laws, right? So this concatenation, I believe, is associative. And concatenating with the empty element gives us back the element we are concatenating with that empty element. So it's like a no-op. And we can rely on those, but we are not going to like describe the laws here. We simply know them by heart. Of course, we can, adding restrictions to this type parameter, we can also use like the syntax from Scala 2, which is like this, but then we need a way to get that implicit value from the context. So we can still use like implicitly, right? We could still do this. Or as a common practice, we define an apply like this, given monoid equals A. So we can say monoid A monoid concat. Oh, using, yes. Given is the when defining instances. Anyway, so let's define one implicit instance. Let's define an instance for strings. So for string, and we define a monoid. Yeah. Something like this. What does it want? I'm not entirely familiar with the Scala 3 syntax. I'm going to be honest with you. I'm presenting to you Scala 3, but I'm not entirely familiar with it. So now we've defined an instance for monoid. In Scala 2, this would have been implicit val something for string. Now we are doing a given, right? This is like the new keyword, using and given, to like pretend that we are not using implicit parameters, but we still do. So, oh no, yes, it compiles. If it compiles, it works. Now, this would be a good definition, but there is one thing missing. In this concat here is like it's a little awkward because it's described as a function, but in Scala we work with methods. And what we do in Scala 2 in order to add syntax to these type class definitions is to like describe a class ops that takes a value of A and its restriction, and then defines a plus plus on it other that concatenates them of our value with other. Well, let's name this self. And now it's nice and Pythonic. And then, because this can't be an implicit class, by the way, for defining like extension methods, because we take two values here. We take our value, our self, and we take our implicit parameter, which is the restriction of the type parameter. So what type level cats is doing, the library, is to define an implicit conversion, like implicit convert to ops, something like this, where it takes how does it do it? Yeah, it takes an A and its restriction, and it returns an ops of A, new ops A, something like this, which is awful, right? This is like boilerplate that you need to write. It's absolutely awful. And also you have problems with it because you probably you'll have problems with it in type class hierarchies. So you have to like have a syntax object from which you import everything, all of those ops, implicits and classes that are meant to add extension methods to our type classes, right? So what Scala 3 introduces is the ability to define extension methods on these type classes. So we can say extension starting from a self, and then we can say we can add a ++ extension method on it, other A that returns an A, and we can say concat self other. And now, instead of using that concats here, we can say state ++ elem, and it will work because the compiler knows how to find this extension here. So this is what I meant by Scala 3 making it easier to encode these type classes in the language. For one thing, it adds this really natural syntax for adding extension methods such that we can do this, right? So this ++ is not a method in the object-oriented sense. It's an extension method that is found by the compiler here, right? Which is really nice. I'm not sure if there are any questions thus far. Are there?
No, there are quite a few discussions. Like for Ayush earlier, there is no direct question that I can see.
Mm-hmm.
And I can tell you, I went to the French system. I'm French. I didn't learn about monowin in high school. A bit later.
I mean, yeah, we learn a lot of theory and not enough practice, let's say.
Yeah.
So yeah, we learned about monoids in high school. I was at a math and computer science intensive class in high school, but yeah, I think it was 12th grade, and I learned about semigroups and rings and all of those awesome algebraic structures. They tormented us with those. So,
we have those just at the last year of high school if you're a math, what do you call that? Major in math. Anyways, keep going. Thanks.
Yeah. So now we can say exercise. We could say monoid sum all concatal list hello world, right? And now let's do it actually here. Yeah, here it's better. This would be like the worksheet. Let's see what. Yay, hello world. We just did a hello world using monoids. How cool is that? Yes. But we would also like to like sum up, combine integers. I mean, 10, 100, 1000. But if we try to run this, This would be, wait. Let's do it here. Yeah. So the compiler says no implicit argument of type monoid int was found. So we must have an instance of monoid for integers. And we can define one really fast for int monoid int new monoid. Yay. So we start from 0. And we can say x plus y. By the way, defining a monoid for int is not necessarily correct because there are multiple monoids possible for int. So I mean, if you can also have products multiplication with the empty element being 1, right? You can also have, I believe, x to the power of y. Anyway, so there are multiple monoids possible, and having a default one is not necessarily a good idea, but let's skip that. So now this exercise should work, right? Yeah, it compiles. So we could like copy paste this in our worksheet. Yeah, let's see what it does. Yes, we now know how to sum up a bunch of integers together. Progress. This is progress. Anyway, now would be a good time in our presentation to talk about how we should define type classes. Like these are a bunch of rules that you need to follow because you are going into the real deal here, right? So type classes must take type parameters, meaning generic type parameters. If it doesn't have a generic type parameter, it's not a type class. Type classes must not keep state, and we'll get to that in a moment. So if your type class instance has a database connection or something, or access to some shared memory location, that's not a type class. That's an object. And you shouldn't pretend that it's a type class, and this matters. It's important to have your terminology correct. Type class instances must be coherent. This may be a best practice that I'm not going to go into tonight, but it's about correctness. Really quick, if you have an ordering instance that you're going to use with a sorted set, you need to be using that ordering instance everywhere, right? It should be like in ascending order or in descending order. But if you have two ordering instances defined for the same type parameter, that may be a problem. You can do it, but you need to encapsulate those orphaned instances really well. Orphaned instance means that it's defined separately from your types, so you can import it later, and it might be a duplicate, right? So be careful with orphaned instances, encapsulate them well. And this last rule that I'm recommending to those trying out type classes is to use the principle of least power. When you end up learning about type classes and their expressive power, you will want to use them everywhere, and that's a bad idea. Scala is primarily an object-oriented language, and it's best if you kept to OOP as long as possible. Type classes come from a different realm, and it's great that we can express them in Scala. Scala is a great language because of that. This is the feature that makes Scala worthwhile. I wouldn't be using Scala without the ability to express type classes, by the way. So, but yeah, default to OOP. And if you need type classes, you need to be able to defend your choice. I use a type class here because I want to compose types. This is the reason, right? Composability, of defining a protocol for composing things. That's what type classes usually define. Anyway, let's go to the second exercise. And Julian, if there are any questions, feel free to ask.
There are two right now.
Yeah.
I don't know if they're directly related. The first one is, does Scala 3 support coherence of type classes? I don't know if you answered that one.
No. I mean, the compiler doesn't do anything to check that you have only one instance for a type parameter defined in your project. It will trigger errors in case it finds two instances in the same scope with the same score, let's say. It will trigger an error in that case, but that's obviously not enough. You need to apply this as a best practice using discipline. This is a bad word in my. I mean, this is a bad advice. Like, use discipline. Discipline sucks, right? But yeah,
no, I
we need to use discipline. But there is a nice. I get a nice feeling in knowing that Haskell developers haven't figured this out either, because GAC doesn't protect well against globally unique instances either. I mean, it has issues when you compile multiple modules together. And you can have different instances defined in two separate modules, let's say, and this is about linking modules together, and it doesn't protect against those. But yeah, this is a best practice. Okay. And sometimes we want to define, we want to break this rule. So rules are meant to be broken, right? Sometimes we want to break it, but usually we shouldn't, and we should use opaque types, new types for that. I mean, you define the new type, like another int or whatever, and then define instances for those. But this is a subject that I may not go into tonight.
Okay, thanks. Keep going.
Cool. Yeah. So let's go and implement equality. And we will right now talk about a superpower that type classes have. You know, if you, I think I have like, yes. We are going to talk about a superpower that type classes have in a minute. So this would be a type class that defines equality. In Scala, we work with equality by calling equals on object, on any, right? But that kind of sucks. So we could define here a helper method like from universal equality. Universal equality sucks because you can compare any two things together, and it's really type unsafe, in case you were wondering. Now, truth be told, Scala does introduce a can equal type class. That in case you enable a compiler option, it will check whether two things can be compared together by having a can equal instance. This is just a compiler trick. It's not can equal doesn't come with anything useful that we can use. This is basically used for evidence, right? It's an unused evidence, let's say. But I'm putting it here in order to say that, okay, we have, I'm not even sure if this helps. I mean, can equal A and A. I mean, two things should be, but anyway, maybe we have like some reference. Maybe we have some class with reference equality that we don't want to compare like this. Anyway, so we can define it like this. And now we are using Scala's like universal equality, and this is just a helper. We are not going to do this, right? This defeats the purpose of this type class. That's bad. This is just a helper. No implicit instance is defined by default like that. But we could, you know, define like equal for any val. For any val, where we take an A that any vals are basically primitives and other types that we don't like to talk about. So Yeah, I mean int long. Yeah. And we could also say using can equal, because why not? Equal A, and we can say from universal equality A. And now we know how to check whether two integers or floats are equal. But we should define like an extension here. We could like do like JavaScript does and have an equality with 3 equal signs. Right? And this is pretty cool right now. Let's also do for string. I changed my keyboard shortcuts to those of Vim, and I'm still a rookie in Vim shortcuts, so I don't know how to quit my IDE. Yeah, let's go back to our exercise. So we can compare strings. Can we compare strings? What happens here? So it doesn't find the extension method. Let's retry. No. I think, import AQ, no, mine AQ given, something like this. Yes. So it's not necessarily visible. This is one thing you should check. I mean, this triple equals here, the compiler will not know from where to get this when speaking about some concrete types at the call site. But in case we were to define like an are all equal, let's say we want to define something like this. Are all equal, this should return a Boolean. We are going to fold left the list because what else are we going to do? We should, I mean, if it's an empty list, it should be true. No, we need to zip it. Okay, we need to zip that list. And then we are going to fold it. And we start from true because if it's an empty list, it should be true. And this would be the result. Okay. Case result X, Y, and this would be equal Y. So we are using the triple equals here, and it works. Even if we delete this import here, it will say our syntax. So yeah, this is fine. But here it will not know from where to take this triple equals, so you probably should import it. One strategy would be to have like maybe like an object to export that, but no, it's fine like this. Sometimes I notice the compiler giving really good error messages. Oh, wait. No, it's not this wasn't a problem of syntax. Sorry, this wasn't a problem of syntax. This was a problem that the equality syntax, the equality for a string wasn't found. What? Oh, okay. So if it can see that in scope it has like an implicit for like an instance for a vacuous string, then it can translate that syntax. I don't know what it does, but anyway, sometimes you have to do imports for importing those extension methods. And maybe you can define like a syntax object that has all the syntax that you need. And this is basically the strategy that Cats has been using. So in Cats, you would like import Cats, syntax, all. But I hope that using Scala 3, we will do this less and less often, let's say. Anyway, so this import .aq.given here, by the way, this given here means that I want to import the implicit instances, the given values in that companion object. And just those, because if I import aq._, what would happen in Scala 2 is that it would import everything, and this could break your code. Why? Because developers wouldn't respect that rule of defining globally unique type class instances. So you could like import an ordering or maybe an execution context by mistake or stuff like that. So this blanket like importing of everything would sometimes lead to unexpected results, which is why in order to import the implicits, the given values, you have to be explicit about it. So, and it's .given instead of ._ for, yeah. Now we are going back. I mean, I mentioned a type class superpower. Superpower because we can derive instances. This is something that we cannot do with plain object-oriented programming. We can derive instances like if we know how to compare primitives like strings and ints and longs. We can also compare lists of ints, right? So we could define for list an equality for lists, right? And we could say any. Let's piggyback on iterable here. Yeah. Okay. Q of M. And A. Well, first of all, we compare the lengths. This is horrible, of course. Like, don't do this, but this is for our purposes. So how should we say it? So it's equals, and then we are going to do like, and then we are going to say for all zip y for all here we are missing the restriction, right? Given aq of A. We can say like x triple equals y. And we can also say a triple equals here. Why not? You know how to do that. What's going on here? Found the what? Yes. What? What did I do? What? Ah! Oh my God, compiler errors. And why is this not working? And in a presentation, don't do complicated examples like freaking lists.
No, I have to say, I admire you to do the live coding at 6 p.m. on YouTube. I wouldn't have dared it. No, I'm afraid I can't help you much, though.
Yeah. Wait. Yeah.
It's the second time that Safta is trying to help you. I saw him ping you on Teams as well. Next time we should invite him to debug.
Yeah. Okay. Here, so given equal away. Yeah.
And Safta is saying to use using instead of given.
Oh shit! Oh my god! Yes, I'm learning Scala 3 right now.
Made it.
Awesome.
Okay, next meetup you're in, we'll invite you.
Yes. So anyway, we can derive stuff for lists, but and this is like a type class superpower. We can derive stuff. We can derive stuff for tuples. I mean, we could define instances for tuples but we can go further than this, right? Now, I'm going to get into a complicated topic right now because this is a feature that is basically replacing macros. In Scala 2, if we want to derive, for example, if we want to derive equality for case classes or for products like tuples or for sealed traits like enums, we would have to use a library that is powered by macros. So we would have to use something like shapeless. Let's see, I'm like by Miles Sabin, or we would, I think there was also Magnolia. Let's say real-time searching. Yeah, I think this was, I never used this, right? So fast, easy, and transparent type class derivation for Scala 2. I never used this one. I used shapeless, and I crashed my compiler several times until I gave up when trying to derive instances for type classes. But what we can do, and now I'm going to cheat, right? I have like the code here because this is like complicated and I don't necessarily understand all of it, how this works. Basically, we have the same definitions as before, except now we have this derived given. Now, what this does, this is basically like a protocol that the compiler has, like, you know, how the compiler also uses flat map as a protocol in for expressions. Well, we can, let me show you an example here. We can say like case class user, which has a name and an age, and we can say derives equality. And this is this instructs the compiler to look for that an inline definition of derive, which would be this one, this derived here. And this would use compile time reflection to look look at the instances, to look at the types involved. And according to type theory, we can have like two kind of types. So we can have sum types, or we could have product types. Product types are tuples, and case classes. Case classes are basically named tuples, right? And sum types are enums, sealed traits. So those are the sums. And depending on the case, we do some compile time magic here, which replace the awful macros that we've been using. And but if you'll take a look at this implementation, it ends up doing type erasure at some point and doing some unsafe stuff. But it usually works. I mean, okay, let's go for equality sum. What does it do? Yeah, no, the one piece of magic is in this sum on all, which basically takes the type, decomposes it into parts, like being expressed as a tuple, right? All the magic is basically in this mirror of. So this mirror of decomposes your type, and you can like reflect on its definition. Basically, you get a tuple that represent the fields you have. Like in a case class, you would get the field names along with the field values, and you would get these as tuples. And you can then go over those fields and compare them one by one. Like we want to express equality, we would compare the fields one by one. There's a little unsafety here, and I don't necessarily understand how this mirror works. I would have to look into it. Basically, I went to the type class derivation article here, and I copied the code and made it work. And which is what you would do when it comes to compile time reflection. You copy some example, you cargo cult it, and then you would bang it with a hammer until it works. It was, I would have to say, it was amazingly easy to make this work compared to what I had to do in Scala 2. I'm pretty sure that for more complicated cases, you would still need the library. But for equality here, we don't need the library. So now this user here, we know how to compare users because we simply said derives equality, and then the compiler did its magic. And now we don't need macros anymore. We just need this compile time reflection thing that is meant for deriving type classes. So this was one missing feature from Scala 2, the ability to automatically derive type classes, which is awesome because this is like a type class superpower, as I said. And of course, we can like do user Alex age 13 because I am. That's how I feel sometimes. And this would not trigger, hopefully, any. Yeah, this is like a warning about the indentation. As you've noticed, I haven't used the new indentation-based syntax because I'm not sure if I like it, but I'm getting there. So yeah, this should be correct right now. Maybe it's complaining about, no, it's fine. Yeah. So we can now derive stuff, right? Any questions thus far?
Still no questions.
Yeah.
I do have one, actually.
Yeah.
So I'm following along. I can kind of following what you're doing. I'm wondering, do you have any example of practical use case where that is needed?
Yeah. I'm glad you asked. This is what we are using in our code. So we have a type class called log show. As you know, in a bank, logging sensitive data is not something that we want to do. So what we did with Scala 2, not Scala 3, but with Scala 3, this is much better, right? In Scala 2, what we did, we installed a linter that basically bans to string in the project. So we no longer can print line, and then you give it an object that contains the user's private personal information there, right? And it's his IBAN or whatever. So in order to log stuff, we need to define a log show instance for that type. And we have defined like a type safe wrapper around our logger interface, around logback. That only works with this log show instance. So we can no longer log any value. We only log those values that have a log show instance defined. And by the way, string does not have a log show instance defined by default in our project. Okay. How would this work? You would have like a log show function that gives you a log show message. And this log show message basically resembles YAML. We can like serialize strings, we can serialize maps, we can serialize lists, we can serialize exceptions because this is for logging and we should be able to log exceptions. And then the wrapper would take this data structure and do some nice formatting, and then use logback under the hood to log this data structure, right? So it also does some beautification of what it logs. And of course, defining log show instances for the types that we care about is kind of exhausting. And this ability to derive instances is great, right? So you have a log show for the user, let's say, anyway, for a bunch of fields, and you are then able to define a case class that has all of those fields that are maybe part of the request. Some of those fields may be sensitive, but in that case, we log them with wildcards instead of like showing the actual value. Like we are not throwing the user zban in our logs. We are going to log like wildcards, right? So yeah. And by the way, this case empty here is interesting. We need empty. Why? Because in order to derive type class instances for our types, we need the ability to combine, to take like different instances and combine them together. This is about composition. So you basically need to define a monoid instance for this one. I mean, in order to work with this, comfortably, let's say. Because, for example, you get like two case classes, and you want to derive an instance from those two case classes. You receive them as a tuple, right? What can you do? You can make a list of them, right? So you need some ability to take like one log message and another log message, and then combine them together in a list of log messages. Let's say you get a case class. You can serialize that as a map. Well, what happens when you like try to combine two case classes together, which are maps? You might do concatenation of maps, or you might unify them as a list. There are some choices you can make there, like what would you do when you serialize YAML or something. So this is another by the way, here, this isn't necessarily going to be used in generic code. You can simply define empty, and you can define concat as methods or whatever on the log message object and companion object. We don't necessarily need generic code for log message, but this monoid also gives us a name for what we are trying to do, because it's also like we can think of it like a design patterns. Oh, this log message needs to implement a monoid in order for us to be able to combine log messages together. So this is why empty exists, because we need an empty here, right? This is like an interesting design that show. I mean, why is empty? Do you need to log empty log messages? Well, yeah, we need empty in order to combine log messages together. Anyway.
Okay.
So
thanks.
Moving on.
Someone was asking, why is your code inline? But I don't know. I don't understand the question myself.
Inline? What do you mean inline?
Yeah, exactly.
Here? Anyway.
Yeah, let's. If you can expand on the question, then I'm happy to post it again.
No, inline. So there's a keyword inline. Yes, great question. Yes, wait. No, yes. So inline.
Oh, this one. Okay.
Yes, this is another use case for macros in Scala 2. The ability to like dump a bunch of code at the call site. So this is not a normal function. This gets expanded. It's sort of like a macro, right? But it's like a safe macro because the compiler knows how to inline stuff. So you can for one define functions that don't have the overhead of a call site, of a function call site, and sometimes that helps when you have like a when you take, for example, when you have a higher order function and you take a function as a parameter and you dump that in a hot loop, for example, and that would help performance. Sometimes, not always, because the JVM is pretty smart and sometimes inline doesn't help. But here, this is compile time magic, compile time reflection, it's called. And we need inlining for it to work because this is not a normal function. This is basically a macro, but it's like a, safer macro, let's say, than what we had in. It's not a macro per se, but it solves one use case we had with macros in Scala 2. Not sure if that answered the question or made any sense whatsoever. So,
yes. All right.
Yeah. Now, where would we be as functional programmers if we did not talk about functors? Let's implement the functor hierarchy because this is fun. Now, functor F. Now, as you'll notice, we are now using hierarchy types. So we are talking about generic types that on their own have type parameters. When we have type classes in the language, we end up wanting to talk about hierarchy types. And in Kotlin, for example, because it doesn't have a hierarchy types in the language for the moment, they do a weird encoding, which sucks. Inspired by OCaml, and it's also been used in that TypeScript project for functional programming called FPTS. But it's better if you have hierarchy types in the language, and this goes hand in hand together with type classes. If you don't encode type classes in the language, there's less need for hierarchy types. So these two kind of go hand in hand together, let's say. Now, functor, what can F be here? Let's say F can be a list, right? So F of A could be a list of A. Right, so list takes a type parameter, a generic type parameter. F of A could also be option of A. Let's do it like this. Option of A, some samples here, right? Future of A, why not? Try of A, and many other types. So all of this takes a type parameter, and so we need to express that here. Now, what does functor do? Well, functor is something that defines a map. Let's define it directly as an extension, because why not? This one takes a type parameter of A, self F of A, and we define a map as an extension method that takes a function as a parameter that takes as input A, returns B's, and then transform these. So this is like the regular map that you see everywhere in Scala, right? And we can now express this as a type. In less expressive programming languages, we talk about design patterns because we cannot express design patterns as types. Well, in Scala, we often can talk about types instead of design patterns. So here it is. Here is functor, right? Now, of course, this functor here, we may have been able to express as an OOP interface, but things get more complicated further down the hierarchy. Let's define applicative. And this extends functor, because we are adding new stuff to it, new methods to it. And what are we going to add? Well, we are going to add a type constructor, which is pure. This would be the ability to like wrap values in our F. So think of, list one. This would be like, this would wrap an element in a list, right? Or sum of A in an option, or right of A in for either, or I don't know, future successful of A for future, right? So this is pure. And we also need another extension. And not an extension, maybe this one shouldn't be an extension. So we are going to define a map2 operation that take A as B as type parameters. So we are going to take an f of A and an f of B, and then we are going to return, oh no, we are going to also take another function that takes a tuple and then return C. We need C. And then we are going to return an f of C. Now this, as you can see, things get more abstract. I mean, what does map do resemble in the real world? When the answer is nothing. I mean, you don't need to, when thinking of applicative, don't necessarily think about real world objects. You need to think about the operations themselves. Well, what could map2 be? Well, for example, map2 could take two future values and combine them together, or two option values and combine them together. So this is about composing two values that are given to you in a NEF context, right? So two futures, two options, two either values, two lists, why not? And as you can see, the signature tells you everything. This function doesn't do sequencing. I mean, it can be implemented with sequencing, but it doesn't specify sequencing in the signature because there is no dependence between these two tasks. So only F depends on A and B, but FA doesn't depend on FB or vice versa. This means that map2 can process things in parallel, right? So this describes parallelism perfectly. If you want a signature for parallelism, this is it, right? Now, let's get to monads. Oh, no, before we get to monads, we can implement map in terms of map2, and we should, because these two functions should probably be coherent, is the word. So extends, how extension? I'm going to have some trouble, like, remembering all of these new keywords. So we can define a map operation that is defined in terms of map2. So we give it our map, we give it FA. Then we wrap some junk with pure. So we create an F of unit. And given A and unit, we return F of A. Right? So we define it in terms of map2 and in terms of pure map. This is why we can say that applicative extends functor, because otherwise we wouldn't have been able to say that necessarily, or maybe it wouldn't have provided much value. But now we can express map2, and we do that. This isn't necessarily good for performance reasons, but it's good for correctness purposes to have this default implementation. Well, now let's define monad. This is like the star of every functional programming conference, and every functional programmer has to write a blog post about monads, like a rule of the universe. So this one defines flat map. Also defined as an extension. Flat map B, we take an F, we take an A, we return a B, an F of B, and the result is going to be an F of B. Extension. Yeah. And now we can define map to in terms of flat map. So we can say, let's copy that from here because my IDE doesn't work well with Scala 3 yet. So we can say override. No, not like that. Override like this. This is not an extension. And we can say, okay, fa flat map a fb map b, and we return f of a and b. Yay! Oh my god, I'm so good at avoiding compiler errors. Yes. Can we define anything else? Well, map is also going to be defined in terms of flat map, of course, because map2 is defined in terms of flat map. So yeah, it transforms. So, and also let's define monad error. So monad error, because I wanted a more complicated example. Julian, how much time do I have?
That's actually a very good question. I don't know when you want to end up. It's 6:30, 7:30 for you here. We still have 40 people. People stay, so they seem to enjoy you.
It's probably my bad jokes and butchering of the English language.
Exactly. Yes. You've been bashing JavaScript a few times, so that helps always. I don't know how much more you have. I don't know how much more you have to do. I feel like you can go all night.
Yes, okay. I'll try to, yeah, good. So monad error is a type class for handling errors. So types that implement monad error have a context that can throw an error in it, right? So we define a raise error here. That takes, so we introduce a second type parameter. This is a type class that has two type parameters, and this makes things a little complicated sometimes, but it's fine. And so we have a raise error here that takes an error and then returns, shoves that error in the F context. And some examples here for monad error types are future, yeah, future failure, either with its left, right? What else? IO, right? IO raise error, if you're familiar with Cat's effect, and task raise error if you're familiar with Monix. What else? Well, this would be like the main types, right? Yeah. And as you can see, like in the case of future, throwing an error in its context basically hides that error. But it's useful because if you get an error, you have nowhere else to throw it to. So yeah. And this is not enough. We also need the ability to expose these errors in the context, right? So we also define an extension, self FOA, and we say handle error with, and we take a function that no, not handle. Okay, no. We are going to go simpler. We are going to do attempt, and then we are going to expose the error as an either. Now this is interesting, right? So in case we have an error, like if we have a future of int and we throw an error in its context, we'll get a future of either of throwable and int, right? And now, okay, this is not correct. No, we shouldn't do this here. Let's define some instances. We define instances for type classes in the companion object. Why do we define them in the companion objects? If we define them in the companion object, they will be globally visible. If you don't define them in the companion object of either the type you want to implement the monad with, or the monad companion object, Scala will not see them without an import. So you will need explicit imports, and those are called orphaned instances. Now we can given option is like in the standard library, it's fine if we define an instance for it here for option monad option monad. Oh, I don't like this repetition. Type of monad, new monad of option. Yes. Okay. So how do we wrap values in option? Well, with some. Careful here, because this is not option apply. Option apply will violate the laws of applicative. Our data constructor is sum. It's not option apply. And then we have our extension. What's really cool about Scala 3 is that these extensions are also methods. They are specified as extensions, but they are also implemented as methods, so you can like override them in implementations. So we get an option of A, and then we have a flat map for it. I learned like this signature by heart because they are so beautiful. F, yes, flat map F. Now, hopefully this will not go into an infinite loop, because the compiler will prioritize the method defined on options instead of going with our extension here. And I know that it won't, so it's fine. Now, we know that option is a monad. We can also define like one for future. I don't want to define one for future. That's for another exercise. But one interesting thing here, we can say with the implicitly function in Scala, we can take an implicit value of a type class, an implicit value from the context, right? So we can find if there is a monad of option instance defined in scope, and this should work, right? But what happens when we say implicitly applicative option? I mean, a monad is an applicative. If you have a monad, you should also have an applicative. So does this work? Well, no. And it says, Scala 3 actually has really helpful error messages here. So it says the following import might fix the problem. This is so awesome. I love this so much. They try to make the errors more friendly. But we have to fix the problem somehow, because like depending on this in a well-designed library is not enough. One way of doing that would be like to go in the companion object of applicative here and say that we want to export the givens of monad. And for our purposes right here, this will be enough. And we can also say that for functor. So we want functors. We want functor to also expose the givens exposed by applicative. And now we could say that we also want a functor of option, and it would be enough. Yes, success with green. Now, I'm not absolutely sure if this will lead to complications or not. I know from my experience of contributing to and looking at the code in CATS that things are never as simple as this, because you often end up in conflicts. Now, should conflicts happen, another way, instead of doing like this sort of inheritance of implicit instances, we could define like an instances object and export them there. So we can export everything in like an instances object, and then we can import from the givens from this object. But this will not be globally available. This would be another strategy that is more explicit. So you put every type class instance you have like in a special object that you import wherever you need to import it. But for our purposes here, exposing the implicits of exposing the implicits like this works. And now we get to monad error. Let's define a monad error for either. No, let's define one for future first. Monad error, future, and throwable. Right, new monad error. Repetition. Implement. Yeah. Future failed. E. We also have override pure. Future successful, not apply. Why? Because it will catch errors and violate the laws of monad. So not apply, right? Future successful because we need the evaluation here to be strict. What? Why? Oh, we haven't extended monad. What we should. Okay, and now we also need an extension. And here things get complicated for future because we will need an execution context, unfortunately. So we will have to take one from our context given using execution context. And we will have to take like self. Oh no, I don't have like useful IntelliSense here. No, I don't know how to do this on future. Wait, Scala future. No, not future and promises. Wait, not that. Here. Yes, this is it. I think it's like, okay, I think I know it. Wait. So we can do like map and wrap it in a neither. Yes, in a neither like this. And then we can do like recover with, no, recover, that's recover. And we can do like, like this. We can write it in on the left. No, not. Transform. Wow, transform with, okay. This is a try, so we are going to do a tweezer. Should work. No. Oh, transform, just plain transform. Doing type Tetris, I'm sorry about this. My idea is not helping. Okay, and we also need to define flat map, def flat map. And I'm pretty sure that you're going to learn all of these definitions by heart tonight, because I'm repeating them. Okay, self flat map F. Yay, green. Yes, we have a monad error for future. And now we know how to handle errors. And we could have also defined an instance for either, and this one is more complicated. Why? Because either takes two type parameters. So we would say monad error of, and our hierarchy in the type in monad error takes one type parameter, and either has two type parameters. So what we need to define here is what is called the type lambda, that goes like this. Oh, here we also have a type parameter for e. So it goes like this, and we define a monad error like that. Okay, and I'm not going to bother defining this instance here. That's left as an exercise for the reader. So what this type lambda does is to make like a type projection. This was also possible in Scala 2. So Scala kind projector. So this useful compiler plugin works for Scala 2 for defining like a nice syntax, which avoids you to do like this awful type projector. So we can do type projections like this in Scala 2. And this compiler gives us a nicer syntax to work with, which is like this, lambda something. But Scala 3 comes with a nicer syntax for this. And now we can work like this, right? I mean, this type projection basically talks about either as if it had one type parameter, because e, our error type, is already known. So that's the trick that we are doing here. And of course, we can also export the givens in monad error, because the monad error is a monad. So now we know how to handle, for example, future. I mean, if we go like in this exercise through here and we say implicitly a monad of future, it could work. No, it doesn't work. Ah, yes, because I also need, and I cheated here, right? I mean, I told you that type classes should not have state in them. Well, for future we cheat. Future is like a bad monadic type, right? So we import our implicit execution context, and then we can have like our monad instance. Let's see. I think I'm not going to go into exercise 4 today. I had like an interesting exercise because it's getting late. What I'm going to do is I'm going to define these functions, because now we have monads. What are we going to do with monads, right? Let's do something interesting. The point of having types, of being able to talk about monad in your code, is the ability to define generic code that uses those interfaces. So we could define like a sequence that takes any f. This could be like future, or it could be option, or it could be either, it could be IO, task, or whatever. And we could take a list of f of a. Also need a as type parameter here, and we could return f of list of a. So we turn the we expose the f within, right? So think about this is basically the signature of future sequence. So you are given like a bunch of future 1, future 2, future 3, and you are getting back a future list of A, right? So instead of a list of futures, you get a future of a list. But this allows us to express, monad allows us to express this generically. We could say given monad. Now, what are we going to do with list? Fold it, of course. Oh, no, this isn't given. I'm mixing these keywords up again using. So we are going to start from an empty list, empty array. And then we are going to have an accumulator and a task, right? Now, what can we do with this? Well, we can like work with flat map. So flat map, and this is our list that we are building, and then we can like task map, and this is would be like a result, and then we would say we would append to our list. Oh, not yeah. Yes. Now it should be fine. Yes. And this implementation is correct right now. How do I know? Because it compiles. Yeah. But there is, I want you to pay attention here. There isn't any actual dependence between the types involved. So flat map is too strong of an operation here. We can also work with map too. So we could say, instead of depending on monad, we could depend just on applicative. And what does applicative expose? Applicative expose is map to. Let's use it like this. And we would give it our accumulator and our task, and it would give us back a list and an A, and then we would combine them like this. Syntax error. Yeah. What? Yeah. Sorry. We have an applicative of F here. No. Yes. We are working with applicative right now, not monad. Yes, it compiles. But we are working with lists here. And we need one final step, because list is basically a stack, and it's going to give us that list in reverse order. And that's not good. So we do need to introduce sequencing, right? So we would have like, no, not, I'm talking nonsense. Sorry. No, we do a final map. List reverse. And Dijkstra is not happy about my algorithmic complexity here, but it's fine. Anyway, so this would be like the generic function that works with any monadic type, not just futures or not just option or whatever. And I encourage you to check out this really awesome type class from Cats. Let me see, type level Cats traverse. So you will often hear the phrase, the solution was traversed. It was traversed all along, because this traverse is like that sequence, but it's like a sequence on steroids. And it's really useful. And when you hear a functional programmer saying that they love traverse, they are basically saying that they love for loops, because it's a for loop, but it's fancier. Yes. So, but yes, check out this awesome type class and learn how to use it, because it provides some really awesome shortcuts. It's basically for shorter pieces of code, for brevity, right? Instead of defining for loops, why not have cryptic functions? Anyway, so I also had another cool exercise, but I think it's getting late.
We can have another Scala meetup soon.
Yes.
That's also possible.
Yeah. Anyway,
it's funny because last week when we met, I was like 3 hours. It's just crazy. You'll never have a 3-hour meetup. Well, it's actually almost too short.
Yeah, there are many more things to talk about the type classes. I'm also preparing a bigger blog post with best practices that I presented, like my last presentation on Scala Love. I basically had like a 1-year pause for presentations. I did no presentations whatsoever in 2020 due to the pandemic, and now I'm out and, guns blazing. So I also have like a blog post with like a long form blog post with recommendations coming and best practices and so on, where I will talk about more. I will talk about these rules more. So and others. Yeah.
Do send us a link, so I'll put it in the description of the video.
Mm-hmm.
Yeah. Okay. Thanks a lot. Thanks for the people that stuck around. Do you have anything more, Alex? Or am I cutting you, or should we slowly go into the end of the meetup?
We are fine. We are fine. I hope I haven't bored anyone.
I found it increasingly hard to follow. I have been able to tag along for the first half, and then slowly it was like getting out of my usual complexity level. But that's interesting. I think we have still about half the audience we used to have, so that's quite nice. I think, given that it's dinner time for a lot of people.
Mm-hmm.
So I think there's definitely value there, and for all of you, we can always it's going to be online, so we can view it again. That's not going to be a problem.
Yeah. So the takeaway from this is that you should learn how to use type classes. Scala 3 makes type classes better because we can describe the encoding with less boilerplate. The type level class, there's an awesome library in Scala called type level cats from category theory or from cats, which exposes this functor type class hierarchy and many others, and you should check out that one. And it's been ported to Scala 3, so it works with the latest release candidate. You should also play with that. So, and type classes have superpowers, right? But don't misuse them. Yes, that's the.
Thanks a lot, Alex. That was nice to have someone from Romania. Actually, that's one of the good things about the pandemic. It makes it easier to have online events where we meet people from a bit everywhere.
Yeah.
I'm not gonna hold people longer. I will sound like a 15-year-old YouTuber, but I would appreciate if some of you subscribe and like, because it helps me just run more meetups at ING. I have more time. The more successful it is, the better it becomes. So thanks for that, and I hope to see you again next time. You're welcome anytime, Alex, at least to finish your 4th exercise.
Yeah.
All right. Bye, everyone, and see you next time.